I was grabbing a coffee in Hangzhou recently and sat across from a guy who looked like he hadn't slept since the previous decade. He worked for one of the big 100 billion club tech giants, Alibaba or ByteDance, I wouldn't specify. But he wasn't looking at stock prices or ChatGPT prompts on his phone. Instead, he was obsessively watching a grainy, real-time thermal feed of a liquid cooling system in a data center 3 provinces away. He told me, "Everyone thinks we're building intelligence. We're not. We're building a digital furnace." He laughed when I mentioned the latest Silicon Valley debate over AI ethics or boardroom drama. To him, that was just PPT theater, expensive, performative noise. He pulled up a spreadsheet that wasn't full of code, but rather raw electricity consumption metrics and concrete pouring schedules. In the West, he said, they argue about what the AI should say. Here, we're making sure the AI has a body to live in. It was a jarring shift. We've been told the AI race is a battle of wits. Who has the cleverest algorithm or the most charismatic CEO? But watching him celebrate a 2% drop in server temperature, like it was an Olympic gold medal, made me realize we've been looking at the wrong map. While one side of the world is caught in a loop of litigation and technophobia, the other is treating computing power with the same brutal material urgency as the 19th century steel rush. This isn't a software update, it's a physical reallocation of global power. In 2025, the 100 billion club isn't just buying chips. They are stacking reinforced concrete and silicon to create what can only be described as computing power sovereignty. The question isn't who has the best story anymore, it's who has the most voltage.
Wow. That image of the digital furnace, it's the perfect way to frame this. It's a much-needed splash of cold water, really.
It really felt that way. It was a total reality check.
For so long, we've treated this AI race as this abstract conceptual thing, a battle over code, or who gets the latest funding round, or these theoretical alignment debates.
Right, the PPT theater.
Exactly. But what you saw and what our deep dive today confirms is this massive pivot. It's a shift toward hard physical infrastructure. The digital furnace is real, and the whole game is becoming fundamentally material.
Okay, so let's unpack all of that. We've got this incredible set of sources that really detail these material foundations of what looks like a new kind of arms race. What's our mission today? What are we trying to figure out?
Our mission is to get past those abstract discussions. We need to analyze the 3 non-negotiable physical pillars that are holding up this whole idea of computing power sovereignty.
Key pillars, okay.
Right. We're looking at a system built from the ground up. So first, it's the command of electrons. This massive, state-coordinated energy infrastructure. The voltage advantage you just mentioned.
The fuel for the furnace.
Precisely. Second, there's this huge philosophical split. A divergence that favors pragmatic, physical applications over, abstract model debates.
And the third?
The third is the engine that runs it all. An unparalleled supply of human capital. The actual engineers and scientists building this stuff.
So we're not just looking at the code, we're actually tracing the concrete, the electrons, and the educational systems that produce the people who do the work.
That's it. We're going to analyze the strategies that are providing this, frankly, decisive advantage in energy. Then we'll contrast that instrumental focus on physical applications against the Western emphasis on large language models. And finally, we'll get into the sheer scale and quality of that human talent pipeline. It's the complete picture of what national technological resilience looks like in 2025.
Let's dive in. Let's start with the most basic brute force piece of this puzzle, power. If AI is a furnace, then the fuel, the electricity, is the ultimate bottleneck.
It is. For decades, we were all obsessed with Moore's law, with chip density, but now, it sounds like the real constraint is just getting enough juice.
So what changed? Why now?
Well, what's fascinating is we've broken this kind of historical energy equilibrium. For years, you had chip manufacturers like NVIDIA getting better and better at GPU efficiency. So processing power went way up, but the energy you needed for each calculation was actually going down.
That kept things manageable.
It kept the lid on it, yeah. But the shift to these massive, and I mean massive, power-hungry AI models, we're talking multi-trillion parameter models, it just completely broke that balance.
So it's a kind of Jevons paradox. The more efficient it gets, the more we use it, and the gains are just wiped out by the sheer volume.
That's a perfect way to put it. The models got so big, so fast, that any of those efficiency gains from the hardware side were just immediately swallowed up.
Okay, give us a sense of that scale. What does it look like in real terms?
The numbers are, they're genuinely shocking. If you take the training of GPT-4, it's estimated to have used over 50 gigawatt hours of electricity.
50 gigawatt hours. I have no idea what that means.
Okay, to put that in perspective for you, that's enough electricity to power the entire city of San Francisco for 3 full days.
Wow. Okay. Just for one training run?
For one model.
Yeah.
And if you look ahead, the projections are even more stark. By 2028, some analysts are projecting that AI alone will consume as much electricity annually as 22% of all U.S. households combined.
That's staggering. It completely reframes energy, doesn't it? It's not just a cost input anymore. It becomes a strategic resource, a competitive weapon even.
It absolutely will. Energy is quickly becoming the binding constraint. It could even eclipse talent and capital as the main limiting factor. I mean, if you can't get the electrons, you can't run the models.
You can't iterate, you can't improve.
You certainly can't serve 1 billion users with some kind of real-time AI agent. The physical capacity of your grid literally dictates the ceiling of your digital ambition.
Which brings us to this enormous advantage you get from a coordinated national strategy. When we look at China's approach, it's described as a dual-track strategy.
Yeah.
What does that actually mean?
It's a very deliberate, centrally planned approach. And it prioritizes 2 things above all else: velocity and stability. So dual track just means they're pursuing 2 huge goals at the same time.
Okay.
On one track, they're just aggressively deploying clean power solar, wind, nuclear, hydro for their long-term dominance, both technologically and environmentally. But on the other track, and this is the key, they are simultaneously expanding coal and oil production
To make sure the lights never go out.
to guarantee immediate, absolute energy stability. This gives them this unprecedented velocity of construction, and it ensures that those data centers are always fed, even if it means some, temporary environmental trade-offs.
And when you look at the pace of that construction, the numbers are they're glaring. It really highlights the power of that kind of centralized focus versus a more fragmented market.
Oh, the metrics are hard to ignore. Right now, China has 32 nuclear reactors under development.
32?
In the U.S., we've built 2 since 2014.
2.
Or look at solar manufacturing capacity.
Yeah.
The engine for future clean power. China's capacity is over 1,000 gigawatts. The U.S. capacity is around 26 gigawatts.
So you have this combination of a guaranteed stable baseline from fossil fuels plus this massive scale up in renewables. That is a huge structural advantage for anyone trying to build a digital furnace.
It's everything.
That construction velocity makes some of the logistics stories so compelling. I was reading this account from a lead power grid operator. He was stationed out in the Ningxia Desert, which is being converted into this massive computing hub.
Right, one of the keynotes.
And he describes this moment when a new AI cluster comes online and it surges with demand. It instantly needs gigawatts of power.
And that instantaneous surge capacity, that's the whole game right there.
Exactly. And because of the state-coordinated energy strategy, this operator, he didn't have to navigate a market or negotiate rates with different utilities. He just executed a single synchronized directive.
Like a conductor?
He said he felt like he was conducting a silent, perfectly tuned orchestra. He pulled surplus wind energy from the north and hydroelectric from the west, routing it all through these ultra-high voltage UHV lines. So how much of this hard advantage comes down to that UHV network?
The UHV network is, it's the physical manifestation of that command structure. It's seen over $50 billion in investment just since 2021.
So it's new.
Very. Think of it as a dedicated, high-speed, nationwide circulatory system just for digital computation. It's designed to move massive amounts of power over vast distances with minimal loss. This central coordination is what allows an operator, like in that Ningxia example, to execute a single command that instantly reallocates power from a wind farm hundreds of miles away to a data center needing gigawatts.
And that kind of coherence is, basically impossible in a decentralized system.
It's virtually impossible to replicate when you're dealing with multiple private utility companies, different state regulations, market pricing. It's just not designed for that kind of speed and scale.
And that coherence must translate into a staggering cost advantage, which means cheaper compute hours. What's the actual price difference we're talking about?
This is critical because the price of electrons dictates the entire economic model of training these AIs. The sources say Chinese data centers on long-term contracts can get electricity for as low as 3 cents per kilowatt hour.
3 cents?
Now you compare that with major U.S. hubs like in Northern Virginia. Data centers there are paying between 7 and 9 cents per kilowatt hour.
Wow. So if I'm a developer in China, I can run my model for 3 times longer or make it 3 times larger for the exact same cost as my competitor in the U.S.
That's the strategic advantage in a nutshell. It completely changes the economic calculus of running these huge trillion parameter models. And when your primary input electricity is that cheap, you could afford to be less efficient in other areas. And that's crucial for resilience.
And this is all backed by the sheer size of their infrastructure.
Oh, absolutely. China operates the world's largest power grid. In 2024, they're generating more than twice as much electricity as the U.S.
Twice as much.
And the investment is not slowing down. Morgan Stanley is forecasting China will spend something like $560 billion more on grid projects through 2030. And that could result in an estimated 400 gigawatts of spare power capacity.
Spare capacity, just sitting there waiting for the next generation of AI clusters.
Ready and waiting.
This expansion is also being coordinated geographically by this East Data, West Computing policy. It sounds like a logistical masterstroke.
It is. It's a national plan launched in 2021, and it's all about optimizing the footprint of this digital furnace. They're strategically moving new data centers to the huge, sparsely populated western regions of the country.
Why there?
Two main reasons. One, that's where the electricity is cheapest, especially all that surplus renewable energy from wind and hydro. And two, the climate is cooler. That drastically reduces cooling costs, which can be up to 40% of a data center's total energy bill.
And the government smooths the way.
Exactly. The policy gives them incentives like faster approvals, easy land access. It just removes friction and reduces the overall operational cost.
Okay, so this creates a really fascinating trade-off. They're using this abundant, cheap power to mitigate a constraint on another critical resource.
Yeah.
Advanced chips.
Yes, and this is where it gets really interesting. This is true strategic thinking. China is facing constraints on getting the most advanced chips, the top-tier NVIDIA stuff, because of export controls.
Right.
So they compensate by leaning into their biggest advantage, cheap power. They could take large numbers of weaker domestically produced chips and connect them all together to get a comparable level of high performance.
But that approach must use a ton more electricity.
It's computationally very hungry, yes. It requires significantly more electricity. But it becomes economically viable because of those 3-cent electrons.
Can you give us a concrete example of that trade-off in action?
Yeah, the example of Huawei's cloud matrix system is perfect. There's a common AI performance benchmark. And on that measure, the cloud matrix delivers comparable computing power to NVIDIA's flagship system.
Okay, so they're at parity.
On performance, yes. But it needs 4 times the electricity to do it.
4 times?
Now, in a place where power costs 9 cents per kilowatt hour, that's a complete non-starter. Your operating costs would be insane. But when power costs 3 cents, that difference is easily absorbed. They are literally using their voltage advantage to overcome their chip disadvantage. It's technological resilience through sheer scale and economics.
Okay, so if section 1 was about the hardware, the physical concrete, and the electrons, this next section feels like it's about the software, but maybe more the strategic philosophy behind the software.
That's a great way to put it. It's this divergence between an AI that can talk versus an AI that can build.
It goes right back to that guy in Hangzhou. They argue about what the AI should say. Here, we're making sure the AI has a body to live in.
That is the core philosophical split. So much of the Western conversation is focused on alignment, abstract ethics, the output of large language models.
Yeah.
But the strategic focus in the East is on what they call instrumental rationality. It's about pragmatic application in the physical world.
And you can see that instrumental focus so clearly in the sources. They're moving AI off the internet and onto the factory floor.
Yeah.
There's a great example I read about a quality control engineer, a guy named Chen, working in this huge manufacturing plant in Foshan.
The focus is purely on output, right?
Exactly. His team integrated this really pragmatic AI model designed for one thing: microscopic defect detection in aerospace components.
Was that not writing poetry?
No. It doesn't engage in social commentary. It doesn't have woke filters. It just silently scans thousands of parts per minute with incredible precision. And it directly increases the factory's total factor productivity. That's the metric.
Yeah.
How efficiently are your inputs being turned into valuable output?
It's solving physical problems: gravity, friction, heat.
Right. When he watches those robotic arms move, the algorithm is prioritizing material output, not abstract discourse. And that highlights this really deep divergence. It's about building national power through tangible industrial outcomes, which, a clever chatbot just can't do.
The strategic pivot is towards substance, using AI for predictive industrial maintenance, or optimizing these incredibly complex logistics networks, or enhancing manufacturing precision. These are all concrete, measurable problems. They see technology as a tool for societal optimization.
And what's particularly interesting is that this focus is backed by some real intellectual skepticism about the Western model, this obsession with large language models, LLMs, as the one and only path to general artificial intelligence.
Oh, the skepticism among China's leading AI scientists is very pronounced.
Yeah.
You have major figures like Teng Ji, Zhang Yaqin, Zhu Songchun all voicing these serious public critiques, questioning whether just scaling up LLMs can ever really lead to GAI.
So what are their main arguments? What makes them think LLMs are a potential dead end?
Well, there are several big issues they cite. The first one is just high computational inefficiency. We've talked about the power consumption. They see it as a brute force method with marginal intellectual gains.
Okay.
What else? Second, and this is critical, is the lack of embodiment. LLMs are trained on text, on descriptions of the world. They don't interact directly with gravity or friction. The model doesn't truly understand the physical reality it's talking about.
So an LLM can write a perfect paragraph about physics, but it doesn't know how to catch a baseball.
That is a perfect way to put it.
Yeah.
They also point to other problems, like a model's susceptibility to catastrophic forgetting, where learning something new makes it forget old, critical information.
I've seen that happen.
And their weak logical and causal reasoning, and of course their inability to know when they're wrong, the hallucinations.
It really sounds like a philosophical rejection of the whole idea that linguistic competence is the same thing as intelligence. But if they're so skeptical of LLMs, why are they still investing so much in them?
It's a pragmatic hedge. But it's also combined with this deep strategic pursuit of diversified pathways. They're not abandoning LLMs. They recognize they have immense near-term economic use in things like translation, summarization, basic coding help.
Sure.
But strategically, they see the risk of what they call a Western monoculture, where this massive investment is focused almost entirely on one paradigm. If it turns out LLMs are a dead end for true GAI, then that concentration of investment becomes a massive strategic disadvantage. So they invest in LLMs for the immediate gains, but they're heavily funding alternative paths at the same time.
Okay, so let's talk about those alternative paths. They're trying to build the AI's body, not just its voice. What are the key areas of investment besides LLMs?
The state-driven plan is really diversified, and it's explicitly brain-inspired. It's focused on embodiment and efficiency. We can break it down into three main areas. First is what they call embodied models.
What does an embodied model actually look like in practice? Is it a robot?
It could be. These are models trained through reinforcement learning. So through direct physical or simulated interaction with open generalized scenarios. Instead of feeding them a giant text file, you put them in an environment, real or virtual, and they learn by trial and error. They encounter real-world constraints.
So they're learning from experience.
Exactly. For instance, the Beijing Haidian district has a whole plan that is explicitly facilitating research in embodied AI. And that includes a lot of work on humanoid robots. The goal is to ground the AI in the physical reality it's supposed to operate in.
Okay, and the second pathway sounds even more fundamental. It's looking at biology, trying to emulate the brain itself to be more efficient.
That's brain emulation research, and this is critical for solving that computational inefficiency problem we talked about. Scientists are actively researching what are called biologically plausible learning algorithms, specifically something called spike-time synaptic plasticity.
Okay, you're going to have to break down spike-time synaptic plasticity for us. That sounds like pure jargon.
It does, but the concept is pretty intuitive. Think about how your brain learns. Your neurons fire these little electrical pulses, or spikes. And the timing of those spikes is what strengthens or weakens the connections, the synapses between them.
Okay.
Spike-time synaptic plasticity is basically the theory that the precise timing of those spikes is what determines how we form memories and learn things. So researchers are trying to build that biological mechanism into their AI models to replace the current inefficient backbone of neural networks, which is an algorithm called backpropagation.
And backpropagation is the power-hungry part.
It's incredibly computationally costly. If they can find a more efficient, biologically inspired learning rule, they could dramatically reduce the amount of energy it takes to train a model.
It would basically solve the energy problem from Section 1, a quest for efficiency at a biological level. So what's the third path? You said it was more philosophical.
The third is value-driven AI, and it's championed by prominent scientists like Zhu Songchun. This goes way beyond the Western debate about alignment, where you're sort of trying to bolt on fixes after the fact.
Right.
Zhu's argument is that GAI must be value-driven from the ground up and not just data-driven. It needs a cognitive architecture that can assimilate a specific hierarchy of values, not just abstract ethics, to guide its exploration and its decisions.
So you build the values in from the beginning as an internal compass for the AI. How are those values defined?
They're structured in a hierarchy to manage safety and purpose. It starts with elementary self-value, which is just basic survival of the system. Then it moves up through social values like adherence to laws, and finally to group value, which is alignment with the state and collective civilizational interests. The whole framework is designed to manage the AI safety problem internally from the start.
This philosophical difference seems to feed directly into this concept of algorithmic governance. It's like they're building digital traffic rules to enforce this instrumental approach.
That is precisely the role of algorithmic governance in their framework. It's not seen as some kind of bureaucratic restriction. It's seen as a prerequisite for ordered, scalable progress.
And the goal is always productivity.
The overriding goal is enhancing total factor productivity across key sectors, logistics, manufacturing, public services, while consciously trying to avoid what they see as the social fragmentation and awakening culture of Western digital spaces.
Which brings us back to that idea of civilizational resilience, building a kind of national cognitive immune system.
Data and compute sovereignty are intended to form exactly that. The idea is to protect the domestic information ecosystem from what some of our sources call the corrosive, entropic drip of Western digital culture. It's a very conscious, strategic choice to favor material problem solving over abstract discourse. And in doing so, they turn that local cultural trust and centralized control into a competitive advantage.
Okay, we've talked about the hardware, the electrons, we've talked about the software philosophy. Now we have to talk about the final pillar, the human engine.
Yes. The ability to actually execute this massive coordinated strategy, building the data furnaces, pursuing these complex AI models, it all depends entirely on the scale and, critically, the quality of the human capital.
The sources make it really clear that China sees human capital as a core component of comprehensive national power, and they've been prioritizing this for a long time, well before this recent AI boom.
The data on this shows a long historical trend toward dominance in STEM talent generation. China actually surpassed the U.S. in the total number of annual STEM PhD graduates way back in 2007.
Wow.
And the gap has only widened dramatically since then.
So let's focus on the projections for 2025. This is where the scale just becomes almost overwhelming.
By 2025, Chinese universities are projected to produce over 77,000 STEM PhD graduates annually.
77,000. How does that compare to the U.S.?
The U.S. will produce approximately 40,000 total. But the difference is even more stark than that. You have to remember that a huge percentage of those U.S. PhDs are international students. If you look at only domestic U.S. students, China's output will be more than 3 times as high. This is a fundamental difference in the sheer scale of the intellectual workforce being generated every single year.
That is a staggering disparity in the supply chain for advanced technical knowledge. What drove this explosive growth? Was it a single policy?
It's the direct result of a massive, sustained, state-sponsored expansion of higher education. Between 2012 and 2021, the Ministry of Education spending on higher ed roughly doubled. And that investment fueled a nearly 40% increase in the number of new STEM doctoral students just between 2016 and 2019. And that created this huge wave of highly trained graduates that we're now seeing enter the workforce in 2025.
Now, with any kind of rapid expansion like that, the question is always about quality. Is this growth just diluted across a bunch of lower-tier schools, or is it concentrated in their elite institutions?
The evidence really suggests the growth is concentrated where it matters most. About 80% of these PhD graduates come from universities that are administered by the central government. And critically, almost half, about 45%, graduate from what are known as double first class, or DFC universities.
Okay, we need to define DFC. What does double first class actually mean?
Think of DFC universities as the country's most elite, heavily subsidized research institutions. They're sort of the equivalent of the Ivy League combined with the major public research universities, but they're specifically designated for massive national investment. The key point is that the PhD growth is heavily concentrated in these top quality tiers.
So quantity is not coming at the expense of rigor.
Exactly. And you can see that in their rising international reputation. China-based authors are producing an increasingly large share of the top STEM publications. We're talking the top 1% of cited articles. And they already exceed the U.S. in certain specific subfields of AI research. The academic velocity is matching the infrastructure velocity.
This quantitative advantage is also reinforced by a certain mindset, what some analysts are calling the engineer dividend. I was reading a profile of a 2025 graduate from a top polytechnic university in Harbin. He just started at a specialized lab dedicated to autonomous computing clusters.
And what stood out about him?
It was his singular focus. This young man's background wasn't about trying to get a startup exit or chasing social media fame. It was a rigorous, STEM-heavy education that frames technical competence as a core contribution to national technological resilience. He literally sees his work as building something lasting and nationally important, not just as a job.
And that narrative highlights the critical human factor, right?
Yeah.
You have this massive, disciplined workforce that's synchronized by a shared material national goal. This engineered dividend is the human feedstock that makes all the other goals viable. It ensures you get the maximum return on the billions you invested in power grids and data centers because you have the human capital ready to execute.
The collective energy of hundreds of thousands of graduates like that, all trained with a similar rigor and mindset. It allows for a velocity of implementation that's hard to even comprehend in a more fractured system.
It really does. And this brings us to a crucial structural difference: talent retention and sourcing. The U.S. system, historically, has relied very heavily on attracting and retaining international talent to fuel its STEM engine.
Right. We know international students make up a huge percentage of U.S. STEM PhDs.
About 42% between 2010 and 2019. And the U.S. benefited immensely from retaining at least 75% of those international graduates for over a decade. That brain drain from the rest of the world was a massive strategic advantage for the U.S. for a long, long time.
But the Chinese system is building its engine almost entirely domestically.
Correct. The vast majority of PhDs graduating from Chinese universities are Chinese nationals. International students were only about 7% of doctoral enrollments in 2018. China is building its technological resilience on a deeply localized talent engine, which gives it a very different kind of long-term stability and sovereignty over its human capital.
Okay, so if we synthesize these three pillars, the command of electrons, the instrumental focus on the physical world, and this massive engineered dividend, it all merges back into this central concept of computing power sovereignty.
It does. Compute no longer runs on just technological trends. It runs on geopolitics. The future of AI is being determined by which nations can independently secure and control power, chips, and talent.
The foundational material inputs.
Exactly. So the concept of sovereign AI is precisely that. A country's ability to independently develop and deploy AI using its own infrastructure, its own data, its own models, and its own talent. It's about full national control over the entire AI lifecycle.
And this isn't just some theoretical idea anymore. Geopolitical instability is forcing nations and companies to make real, measurable shifts toward self-reliance.
Oh, absolutely. The uncertainties are driving measurable demand for sovereign AI solutions. One survey of business and government leaders found that 61% were more likely to seek sovereign tech solutions, specifically because of escalating geopolitical risks. This fear, this necessity, is creating an enormous market.
Which brings us to that $1.5 trillion estimate for the sovereign AI infrastructure market. That is an astonishing number.
It is, and it's a combination of new money and primarily a redirection of existing capital that's now being accelerated by strategic necessity. Governments and major corporations are realizing they simply cannot afford to be dependent on foreign infrastructure, foreign models, or foreign data flows.
So spending that might have happened over 20 years is now happening in 5.
That's the idea. That $1.5 trillion estimate reflects this global scramble to secure infrastructure before critical dependencies can be exploited. And this trend is only going to grow. By 2028, something like 65% of governments worldwide are expected to add technological sovereignty rules to improve their national independence.
This leads us to the fundamental strategic difference in how this resilience is being built. The whole industrial policy versus free market orthodoxy debate.
Right. China's hardware advantage is rooted in a highly sophisticated state-led industrial support ecosystem. And the key is that this ecosystem adapts to a sector's maturity. They start with R&D subsidies in the early phase, then they shift to operational subsidies as businesses scale up, and finally they bring in consumer subsidies to create massive, predictable demand.
We saw this playbook with solar panels and batteries.
Exactly. It was successful in solar, batteries, high-speed rail, and now it's fueling the AI infrastructure boom.
Yeah.
This state strategy drives a supply chain advantage through localization. It lowers costs, but more importantly, it accelerates what's called learning by doing.
Right, the process knowledge.
The engineers and workers develop this deep internalized process knowledge, and the unit costs just drop exponentially. And this industrial policy-driven speed is demonstrably outpacing traditional corporate models that are stuck on short-term earnings and quarterly reports.
The electric vehicle sector is a perfect recent example of that velocity.
It's a great one. You have Xiaomi launching its SU7 sedan just 4 years after starting the project. And you can contrast that directly with Apple shutting down its decade-long Project Titan with no commercial product to show for it. This integrated, rapid, industrial policy-driven speed is a massive factor.
And this strategic confrontation is now forcing a philosophical shift in countries that have traditionally been all about free market ideology.
It really is. The geopolitical necessity of confronting China's dominance has forced a move toward what you could almost call state-owned enterprises with American characteristics. We're seeing the U.S. government take direct equity stakes in critical domestic producers.
Like in rare earth minerals and lithium.
Exactly. The Department of Defense investing $400 million in rare earth miners. The Department of Energy taking a 5% stake in Lithium Americas. The strategic need to secure the foundational materials for the digital furnace is forcing everyone to set aside strict ideology for strategic survival.
Okay, finally, let's look at where global organizations are actually focusing their sovereignty efforts. The sources point to this major global blind spot in how sovereignty is being applied across the AI stack.
This is maybe the most critical insight for anyone trying to understand this. Sovereign AI means controlling every single layer, from the concrete all the way up to the core intelligence.
And we're not doing that.
Our research shows that globally, organizations are mostly applying sovereignty oversight to the lower, more passive layers. So data at 60%, where the data is physically stored, and infrastructure at 46%, the physical servers and data centers.
But the strategic layers, the core intelligence itself, are being left exposed.
That's the blind spot. The intelligence itself, how the models learn and make decisions, is wide open. So you have a huge number of organizations protecting their data storage, but they're not controlling the software that actually analyzes and makes decisions based on that data. Only 32% of organizations extend sovereignty oversight to their applications, and a shockingly low 22% extend it to the AI models themselves.
So to go back to the furnace analogy, they're securing the fuel supply and the building, but they're not controlling the actual digital furnace itself. They're protecting the storage facility, but not the IP of the engine.
That is the perfect analogy. You can't have sovereign data, but if you're relying on a non-sovereign model to process it, that core intelligence layer is completely vulnerable to dependencies, to IP risks, to misaligned values. The conclusion is pretty clear. The future belongs to those who build it sovereign across all 4 layers: infrastructure, data, applications, and models.
What an incredible deep dive into the material reality of this AI arms race. We started with that image of the digital furnace in Hangzhou, and it really feels like we've confirmed that this race is no longer just intellectual or financial, it is fundamentally physical. We've discussed the 3 pillars. First, the command of electrons through a coordinated energy strategy and that voltage advantage. Second, the instrumental focus on building the physical world with AI, not just abstract models. And third, the engineered dividend, providing that massive talent engine that's required to maintain this system's velocity.
The final synthesis here is clear. The year 2025 marks the definitive end of an epoch that was defined by narrative, abstract ethical debates, and financial speculation. The material infrastructure being laid down right now, the high-speed UHV lines, the data fortresses, the proprietary value-driven models, the integrated energy grids, these are the digital era's foundational public works. This whole transition is defined by the return to the primacy of physical control and algorithmic sovereignty, orchestrated by a civilizational will that is intent on shaping the technological future.